Today I discuss about one important topics, dense sets, which is related to analysis. Basically, this one is important in matrix space. And overall, we also talk about any set is dense in another set or dense in same set. How this one happen, we also talk about in this lecture. Okay, how this dense set is formed, how that means we see some example of a dense set and how some properties of dense sets, and obviously we'll talk about more problems on dense set. Then we will understand about dense set. First we talk about definition of dense set. This one is too easy what we write now, and now we're also familiar with this. Okay, a subset is subset D subset of R. Okay, not R here, X, any set X, not we construct this particular R of a matrix space. Okay, of a matrix space. Here we construct xt, but we just write this one. A subset D subset of X of a matrix space is dense in X, is dense in X if for any point, X belongs to this set X. Okay, if for any point X belongs to this set X and R greater than 0 we have BXR intersection D not equal to 5. Okay, that means any wall containing this point obviously intersection this, then Bx are equal to what we know about it, x difference are x plus r for r greater than 0. Then what happened, this one intersection D not equal to 5. Okay, if bx are defined in another way, then this one is another. Okay, so basically what we get here, we get in another way any non-empty open set, any non-empty open set in X must contain a point of T. Okay, understand? I think all are understand that. These are too easy. Any non-empty open set, obviously. Now we draw these two figures. This one, some set, some neighborhood, some point is here. Obviously this neighborhood contain one point of this set, so we talk about this one is dense set. Okay, all are understand this figure, and obviously here we talk about some neighborhood and obviously some point in this set but not belonging to this neighborhood, so this one is non-dense set. Understand dense or non-dense? What is the difference between dense and non-dense? If we take any neighborhood in any higher, then dense sets obviously contain some non-empty intersection with this neighborhood, and non-dense set means if we take any neighborhood from anywhere, then obviously here empty intersection. Okay, with this set. Now we also is that portion and going to further discussion of another example of dense set. We know about real number set and obviously known about familiar rational number set. Now known that Q is dense in R. Okay, we also established this one first. Okay, how we established this one? This one is too easily I also seen that. Okay, how this one is happen. We talk about x belongs to R. Then what happened? Then obviously, if for r greater than 0, x difference r, x plus r intersection q not equal to phi happen. So bxr intersection q not equal to phi happen. Yes or no? Yes. So this implies that, what implies q is dense in r. Okay, understand or not? I think this one is clearly understand. Okay, now we'll talk about another portion. This portion is so simply r difference q is dense in r. Okay, r difference q is dense in r. So how we talk? Y belongs to r. Then for r greater than 0, the y difference r, y plus r intersection r difference q is not equal to phi. Okay, understand or not? I think understand. Then this implies what? Byr intersection r difference q is not equal to phi. So what happened? So this implies that r difference q is dense in r. Okay, I think all are understand this. Next we discuss about another portion. Okay, we known about one important rational numbers. This one is the dyadic rational. Okay, also someone are known, someone are not known, but first we talk about this rational, then we talk about this rational is dense in R. Okay, so what we write here? We write here dyadic rational. Okay, which is how that means in how this form of rational is a rational number of this form, a rational number of this form m by 2 to the power n, m by 2 to the power n is called a dyadic rational. Okay, then set D of dyadic rational is dense in R. Okay, I have to prove this one now. So we write it in set form in this way. Okay, m by 2 to the power n, where m and n belongs to what? Belongs to here z you write. Okay, or n, then this one is better. Okay, if z, this one is not a problem at all. Then what now we talk this one. Dyadic rational is dense in R. I have to prove that. Okay, this important problem we have proved now. How we prove this? Okay, first we talk about this portion. If a less than b, then what happened? If a less than b, then there exists r belongs to this d. Okay, this one we represent as d. Dyadic rational represent as d. Okay, then r belongs to this d such that a less than r less than b. Okay, happens or not? Happens. So this implies what? If r equal to m by 2 to the power n, then what we get? Then a less than m by 2 to the power n less than b. This implies 2 to the power n a less than m less than 2 to the power n b. Happens or not? Obviously happen. Okay. There is integer m lies between 2 to the power m and a 2 to the power n b. Okay. Then what happened? That means we choose n so large. We choose n so large that 2 to the power n b minus a greater than 1. Okay. Then we talk about this 2 to the power n a 2 to the power n b. In this interval, we obviously there exists m belongs to z such that this hold 2 to the power n a less than m less than 2 to the power n b hold. Yes or no? Yes. So what we get? We get obviously one certain, that means 2a less than m by 2 to the power n less than b. We also do this. Then what we get? We get obviously here any two, that means real number, any two real number, there is one dyadic rational in there is one dyadic rational number. So if AB belongs to R and this open set intersection D not equal to phi, so what we get? We get dyadic rationals is dense in R. Understand? Now we erase that portion and going to another discussion of one example. Okay, one important example. This is also talk about in higher mathematics. Okay, also discuss about now. Erase that portion and going to further discussion of that. Which one we discuss now? We also discuss now there exists a count, that means we know about that q to the power n is dense in r to the power n. We also know that q is dense in r, that means q to the power n is dense in r to the power n. And obviously the set of all such sequence is q to the power n. Okay, then the set of all functions from n to q which is uncountable. Why this one is happen? There is we know about that there is a 1-1 map from the set of functions from n to 2 element set, from n to 2 element set, okay, and from n to 2 element set into the set of functions from n to q, okay. There is one map from between these two, that means function set. Okay, from n to 2 element set, this function set to from n to q, this function set, there is obviously 1-1 map, and this is, that means this one is bijective correspondence with the all subsets of n. then then by Cantor's theorem we know that there is no onto map from a set to its power set. Okay, again we know from Cantor's theorem what there is no onto map from from the set to its power set. Okay, then what happened? Then obviously q to the power n is uncountable. Okay, q to the power n is uncountable. So now we discuss about that q to the power n intersection L2 is obviously uncountable. Okay, q to the power n and intersection L2 is uncountable. Now we also construct another set which is important for us, and we also discuss about this set. Product n belongs to n. Here minus 2 to the power n, 2 to the power minus n, intersection q, subset of L2. Okay, we considered this set. Okay, consider this set, consider the set, this set. Then what we get? We also get in this way. We talk about it. we talk about it. That means some dn. Okay, we erase that portion and going to further discussion of that. We talk about the set dn, the set dn of all sequences where x equal to xm. Okay, and whose terms are rational, whose terms are rational, and obviously xk equal to 0 for k greater than m. Okay, or k greater than n, not m, yeah, m. Okay, then what happened? Then obviously let t equal to union of n belongs to n tn. Okay, then each dn is obviously bijective with q to the power n. Then each dn is bijective with q to the power n. Okay, then hence it is countable, hence it is countable. Okay, then thus d being a countable union of countable set, thus d being a countable union of countable sets, so countable sets, so d be countable. Okay, then we proceed with this. We saw about that d be dense in L2. Okay, now we saw about that dB what dense in L2. How we talk about this? Okay, now we're going to discussion of that, first we take any x belongs to L2, and for epsilon greater than 0, okay, we can find y belongs to this D, obviously such that norm of x difference y norm 2 less than epsilon. Okay, obviously here we also find that what we find, any x belongs to L2 for epsilon greater than 0, we can find y belongs to D such that norm of x difference with y less than epsilon. Okay, then what we get, since x belongs to L2, and there exists n belongs to this capital N such that n equal to 1 to n plus 1 to infinity, norm xn square less than epsilon square by 2. Okay, if x belongs to L2, this means that after n plus 1 term, this square less than equal to epsilon square by 2. Okay, because x belongs to L2 means these summations are obviously less than plus infinity. Okay, so we talk about that. That means n plus 1 term, after n plus 1 term, this one is less than epsilon square by 2. Now we also considered some v equal to, here v, x1 x2 xn, okay, belongs to r to the power n, and since q to the power n is dense in r to the power n, then what happened, then there exists okay, then there exists r equal to r1 r2 rn belongs to q to the power n such that norm of v difference r2 square less than equal to epsilon square by 2. Okay, then what happened, then obviously we now define a sequence y as our portion and going to further discussion of that. Okay, now what happened, then obviously we talk about that this one, we now define a sequence y, okay, such that yk equal to rk for 1 less than equal to k less than equal to capital N, and yk equal to 0 for k greater than n. Okay, then obviously y belongs to this L2. We define this sequence, then what happened, then y belongs to L2 because this one is q to the power n and obviously another term is 0, then y belongs to L2. Okay, now what happened? Now we also talk about that. Then we have norm of x difference y square, norm to square equal to summation this one k equal to 1 to n xk difference rt square plus here summation k equal to n plus 1 to infinity norm of xk square. This less than equal to, we also known about that this 2 equal to what? We talk about this one epsilon square by 2, this one epsilon square by 2, this one epsilon square. Okay, then what we get? We get a sequence y, x difference y is less than epsilon square. X norm of x difference y is square less than epsilon square. Okay, then this implies that norm of x difference y less than epsilon. Okay, where x and y belongs to L2. Okay, so here x is given any number in L2 and y I also choose this number. So what we talk about that? We talk about that D is a countable dense subset of L2. Okay, therefore D is a countable dense subset of L2. We also talk about D equal to what? D equal to union of Tn. Okay, n belongs to n, and this Dn equal to what? Tn equal to, that means m x m are rational and x k greater than n is 0. Okay, then this d is union of Dn, obviously dense subset of L2. This one is one higher dimension example of dense subset we also talk about today. Okay, now we're going to another example, so familiar example. Also, yes, that not example, one property we also discuss in proposition way. Okay, which property or in proposition we write about it? If D subset of X is dense in XD matrix space, then what happens? If and only if every point of X is a limit point. Every point of X is a limit point of D. Okay, so we have to prove that. How we prove it? This one, or we also known about it. We write here proof and talk about D subset of X is dense in X. So let X belongs to X, then we can find VXR intersection D not equal to 5 for R greater than 0. Okay, this implies what? This implies X difference R, X plus R intersection D not equal to 5. So this happens X be a limit point of D. This implies, no, we write here about here, X be an arbitrary point of this capital X. So every point point of x is a limit point of D. Limit point of D. Understand or not? First part we also proved now. Next part we also discuss now. Which part? Obviously every point of x. That means we assume that next part. Okay. We talk about that every point of x is a limit point of D. We write here every point of x is a limit point of D. Limit point of D. Let y belongs to this x. This implies py intersection D not equal to 5 for r greater than 0. For r, greater than 0. Okay, this one is the definition of limit point. Then what happened? This implies that same thing, y difference r, y plus r intersection D not equal to 5. This implies D is dense in X. Okay, so we also prove this portion too easily. Okay, we erase that portion and going to further discussion of another proposition. Okay, now I think all I understand that. Next proposition is so and simple way. We write it now. Let D subset of X is dense in the matrix space. Okay, X. If and only if its closure equal to X. How this one is happen? Okay, same thing we're going to prove of this. First we write this one, D subset of X is dense in X. So let P belongs to X, then B of P R intersection D not equal to 5 for R greater than 0. Then what happened? Then this implies that P difference R, P plus R intersection D not equal to 5. This is easily done. But how we prove that? That means this implies what? This implies this one. P, that means P be a limit point of D. Okay, that means so this implies P belongs to D dash. This implies that what? P belongs to D closure. Okay, this implies X subset of D closure. Understand or not? Understand. So easily we talk about this. Okay, again we talk about further progression. That means how if X belongs to D, this implies X belongs to X, since D is subset of X. So this implies that this, oh no, not this one is not necessary. Okay, because this one is given, obviously not needed here. D subset of X is given. Now we obviously talk about another thing, D dash subset of X. Okay, if to prove this one, then we have done. Okay, D dash subset of X. How this was happen? D is dense in X. Okay, we talk about this one. Let Y belongs to D dash. This means same thing. B Y R intersection D not equal to 5. This implies what? D is dense in D is dense in X. That means Y belongs to X. This implies, that means this one is proved. So D dash subset of X. So what happened? Immediately we know about that D subset of X, and here we getting d dash subset of x. This implies d closure subset of x. So what we get from here, we mark this one marked as 2. Then what we get, x equal to d closure from 1 and 2. We write here from 1 and 2. Understand or not? I think to easily understand this one. Okay, we are done this one. Next we prove this converse part. Also erase that portion and go into this converse part. Okay, how we discuss about that? To easily we discuss about that. First we know about that this one is given. So how we prove? To prove this one, d is dense in x. So what this means? This means this one, bx are intersection d not equal to 5 if x belongs to x. Okay, so d closure equal to x means if let x belongs to x, this implies x belongs to d closure. This implies bxr intersection d not equal to 5. Okay, because if x belongs to d, otherwise x belongs to d dash means this one. So what happened? This implies that d is dense in x. Understand or not? Easily understand. So also discuss today. First we talk about definition of dense set, then we talk about some example of dense set, then we last we talk about two important proposition in dense set. Okay, now we stop here.